Hello, everybody, and welcome to this week's special James Webb Space Telescope edition of our Hubble Hangout. This week we're going to be talking about a recent milestone that was reached in the building of the James Webb Space Telescope, or JWST for short, as I love to call it. And we have people both from Northrop Grumman and Goddard Space Flight Center to help give us some background and to talk about this latest test milestone. You may recall back in the summer, in their facilities in California, the folks at Northrop Grumman have, for the first time, fully deployed the Sunshield, which will be on the orbiting spacecraft. We're going to talk about that test. We're going to talk about what the Sunshield is, and we'll talk about the overall deployment of the James Webb Space Telescope as well. But before I do that, and before I also get to the introductions of everybody here, let me tell you how you can interact with us. If you have questions about the JWST or the deployment or anything about what it may do, its science, we hope that you will interact with us by either using the easiest way is to use the Q&A app that's either both on YouTube and Google+. Another very easy way to do it is to comment on the event page on Google+ and the YouTube events video page itself, because I'm monitoring all of that. Also, we hope you will tweet at us using the Hubble Hangout hashtag. You can also use JWST. We're doing both of those as well. So please tweet, ask your questions, and give us your comments, and we will use them later on. I'm very excited about today because for the first time in a long time, I've got my old friend, Dr. Alberto Conti. Hello, Alberto.
Hey, Tony. It's great to be here again. Long time, indeed.
Used to be an astronomer here at the Institute. Now...
And they stripped him of his rank and sent him out to me.
That's right. And are you still an astronomer? I mean, what are you doing over at Northrop Grumman?
Yeah, I do. My title is a little weird, but I'm still an astrophysicist here at Northrop Grumman, but I'm the innovation manager for business development, so I work on JWST and things that are perhaps in the future after JWST.
Oh, nice. Okay, good. And also with us is the chief engineer from Northrop Grumman, who works on the JWST, Jonathan Ehrenberg. Hi, Jonathan. It's really good to see you for the first time in our hangout.
Hi, nice to be here.
Good. Also, he's back with us, Dr. Mark Clampin. He is the program manager for the James Webb Space Telescope at... No, I'm sorry, you're not your program manager. You're the observatory project scientist for the James Webb Space Telescope at NASA Goddard. Hi, Mark. Welcome back.
Hi, thanks. It's good to be back.
Okay, and also, Scott, driving the internet.
Driving the internet. I will be tweeting all over Hubble Hangout, and I know that NASA Social and NASA Official has been. I'm already seeing some tweets going out, so I wanted to be seeing you guys tweet, and we'll be trying to gather all those questions and comments up.
So let's go ahead and get started. So the James Webb Space Telescope is being built right now, as we speak, in a lot of different places. It's being assembled at NASA Goddard, but it's being built in many different facilities, one of which is Northrop Grumman, and it is the successor to the Hubble Space Telescope. If you haven't heard about it by now, you will certainly be hearing more about it in the future. It's scheduled for launch when, Alberto?
2018, October 2018.
2018, and we'll talk a little bit more about the details of the schedule, how things are going with it, and everything else. But we really want to talk about a really exciting thing that happened last summer, where they, for the first time, the folks at Northrop Grumman have tested and fully deployed the heat shield, which will protect the instruments on the spacecraft itself. And I guess in order to give some people an idea of what we're talking about, for those who have never seen it before, we have an animation of what will happen once the observatory is in space, once it's in orbit. And I tell you, it's amazing what's going to happen here. This is when you fully understand all the stuff that's going to happen after the spacecraft gets into space. Just blows me away every time I see it. So, John, I think what I'd like you to do, if you don't mind, is we have an animation here of the deployment sequence. Can you step us through it just a little bit? What's going to happen to JWST once it launches?
Sure. What you just saw was separation from our launch vehicle and stabilization and unfolding of the solar array. If you watch along the bottom, it shows our position away from Earth, and as you can see, we're passing the moon and still quite stowed. We have a couple of mid-course corrections to add the necessary energy to achieve our orbit, and the blue dot we just left behind is the manned altitude record currently held by Apollo 13. The Sunshield begins to deploy by opening the aft and forward pallets, and the telescope, which was snugged down for launch, moves away about 4 feet from the Sunshield. And what you see is the various covers that protect the membranes unfolding, and the structure, the mid-booms, as we call them, pressing out. They're like a great big old-fashioned car antenna. And then after a suitable waiting period, we reel in the cables and tension the Sunshield, pulling it to its full orientation. Once that's done, as you're going to see in just a second, the telescope begins to deploy the secondary mirror mount, the aft radiator to allow the instruments to vent their heat to space, and then finally the wings. And this is completed roughly about 1 million kilometers or 600,000 miles from Earth.
And if you guys, you can see on the upper part of the screen, just, sort of the elapsed time. We're on day 29 in this animation.
Yes.
So a month after launch, this thing is going to be going through its paces and to become fully deployed in its spot at the L2 point, and we'll talk about what that is in just a minute.
Yeah.
So I don't know if you guys fully got that. I mean, they crammed this whole gigantic observatory into the rocket, and the engineering challenge, one of the biggest ones they've ever had to solve, I think, was how are they going to get something that has the shape of the James Webb Space Telescope into a rocket and out to where it needs to be. And you just saw the plan for it. John, who was responsible for this this design? Was there a group of people, a team of people that came up with all this?
There's a very large team of people that studied it in the early phases and came up with the architecture. Passively cooled, large beryllium mirror telescope, and then the design has significantly matured over the last few years as it went from concept the Sunshield in some way.
Okay, part of you cut out there. I'm not sure if it was. We caught we didn't catch the last part of that, but hopefully we'll be able to fill in the details a little bit later. So the Sunshield. Let's talk about the Sunshield itself a little bit. Kelly, I don't know if you can go into one of the images or maybe the animation where it was fully where the Sunshield was deployed. Can you go to one of those spots there? What's the Sunshield supposed to do? What's its purpose?
The Sunshield purpose is very simple. It makes a nice dark shadow that the telescope lives in, and it allows the telescope to radiate its heat to space to achieve the operating very cold temperatures that the telescope needs to be able to see our targets. So basically, it's a very high-tech parasol.
And so remember, if I can interject here for a second, remember that we build a telescope, to satisfy our science curiosity, if you will. And so Webb, in order to do its job, needs to be extremely cold because it's an infrared telescope. And so in order to do that and to make it in such a way that you don't have expendables, like, for example, gas cooling or so, we made it into a passive telescope. And so the Sunshield, as John just mentioned, is basically that. It's something that produces a very, very peculiar and very predictable shade in which the telescope and all its electronics sit.
Okay, so Kelly has a nice image of it up now. What's it made of? John?
It's made of a plastic called Kapton. The individual layers, the top 4 layers that you can see, are 1/1000th of an inch thick, and the bottom layer is 2/1000ths of an inch thick. If you speak metric, that's 25 microns and 50 microns, roughly the size of a width of a hair. And the coatings that you see here are aluminum, and the bottoms of layers 1 and 2 are coated with the element silicon. So they're very, very thin. They're much thinner than the snack bag that you ate your potato chips out of at lunch. But it's a very similar kind of material.
So
you guys can see that already? How did you know I ate chips at lunch?
Good guess.
It's an advanced telescope, Scott. It really is.
Yeah, it is. It's not even launched yet.
So presumably this stuff is also very lightweight, correct? I mean, if it's that thin.
It's extremely lightweight.
Are you worried at all about ripping or tearing once it's? I mean, how strong is this stuff?
Let's see. We do stress test it on the ground to make sure that it's been made properly. There are ripstop features so that if a rip does occur, it doesn't propagate across the entire Sunshield. And we've also had tested it in the laboratory for micrometeorite impacts to understand how that affects the mechanical integrity. So, we have thought about it in the design. We worry about it to the point where we mitigate that concern inside the design.
I may be way off here, and I'm certain you'll correct me if I'm wrong, but the Kapton, is that the same stuff they used around the Apollo module, the lunar modules, or is that something else?
This is very commonly used insulation material.
So this is pretty old stuff then. I mean, it's been around a while as far as the technology of the material. The material.
Yes.
Okay, you mentioned micrometeorites. How well and you tested it against that? How do they do? I mean, are they gonna stand up?
Let's see. The micrometeorites will penetrate the Sunshield. Those expected values with considerable conservatism is part of the budget. So for the properties that define how well the Sunshield works, we calculate a budget, if you will, and all of the things that degrade those properties. One of those is holes from micrometeorites. That's in our budget. So we have convinced ourselves that even with...
What do you mean budget? Is this just like the allowable...
Yeah, so we have to have a certain amount of reflectivity, and we're allowed a certain amount of transmission from one layer to the next. If we have a hole in it, say from a micrometeorite, that increases the transmission. So we analyze for the thermal performance given a certain set of material properties, reflectance, absorptance, transmissions, emissivity, etc. And we degrade these by introducing the effects of the holes, contamination, and other things, and convince ourselves at the end of life we meet our requirements. So that's how we go about understanding.
Go ahead, Alberto.
No, I was just going to say this also goes to the fact that people might ask why 5 layers and not 35 or 6. I was
just going to get to that. You read my mind.
Right? That's what we do here. Yes. So, but the issue is, as John just mentioned, in order to satisfy the science requirements, you have to model, how your spacecraft behaves, and so 5 layers is a compromise on, in terms of being able to match those requirements. The other thing that we should mention is that the sunshade, the part of the Sunshield that faces the sun is going to get extremely hot. So there's this tremendous gradient that goes from the hot side to the cold side of about order 600 degrees or so. And
hold on. Scott or Kelly, can one of you put up an image showing these layers so we can have it up while he's talking?
Oh, yeah, sure.
Yeah. Just one when viewed from the side or something like that. Perfect. Okay, go ahead.
So all I'm saying is, this is part of what it really means to build a spacecraft and observatory this complex, which is you have to do an extremely sophisticated modeling to understand not only the environment that the telescope would be in terms of temperature, for example, but the environment in terms of micrometeorites. And we have a lot of telescopes and a lot of spacecraft that have been orbiting L2 for some time, so we started to understand that environment better and better, and so our models get better and better. But as John mentioned, all these 5 layers are sort of the minimum required to satisfy those requirements. Take into account, for the fact that we will be struck by micrometeorites. We will have, a certain amount of quite a bit of heat, on the front layer, if you will, the one that faces the sun, and how the heat dissipates. So it's a very complex set of requirements that you have to fold into a complex modeling that you have to do. And I think the team and John and this couple with the scientists, which are perhaps the users at the end, those that are actually requiring what it is good enough for me to do my science, are collaborating on a daily basis to actually make sure that we do satisfy those requirements. And that's why I think the test that we're going to show in a few minutes was critical for this.
Okay, so I've heard this thing called a big giant radiator, where each of the 5 layers actually do a. Can you describe what they mean by that, John? What is it? Why the 5 layers, and what does it do to heat dissipation?
So what happens is the sunlight strikes the first layer, the closest to the sun, layer 1. A lot of that heat is reflected. Some of it is absorbed, and is re-emitted in both directions, both up the stack and back at the sun.
Yeah, Scott has a nice picture up now.
Yeah, and that heat that now is leaving layer 1 and going to see layer 2, most of that gets reflected. And what you can't see in these pictures, because it's hard to see, is there's a very small opening angle, so that the layers actually form tiny V's, allowing the reflected heat to essentially walk out or reflect out and exit through space. And with every successive layer, most of the incident radiation is reflected, a tiny fraction is absorbed, and with each layer the temperature goes down, starting, as Alberto said, at about 90 Celsius, almost the temperature of boiling water, and when we get to the top, it's almost the temperature that's cold enough to liquefy nitrogen.
So that's that spot where in the image that Scott is showing, where these guys are currently standing, is that the coldest spot?
Actually, in the center, believe it or not, that's the warmest spot.
Huh?
I'm looking at the picture.
At it backwards? Where those guys are standing, that's the warmest spot in the telescope?
Yes, because the spacecraft is underneath it. Okay.
Oh, okay. I was upside down. Okay, I thought they were gonna. Okay.
Yeah,
so that's the warmest spot. I get it now.
Right.
I have it upside down.
The tower, the cables, everything that connects the hot side to the cold side comes through the sunshield at that position, and we call that the core. And the core is the warmest part of the sunshield.
Got it. Okay, Dr. Mark Clampin, I want to get you into this real quick. I want to ask you why. Can you tell us a little bit about why this thing needs to be so cold? What is the reason for getting the temperature down so low?
Well, the reason is because this is an infrared telescope, and infrared, as we all know, is heat radiation. And the science goals for this telescope span a broad range of infrared astronomy, ranging from looking trying to take images of the very first galaxies that formed in the universe to understanding the nature of the atmospheres of exoplanets. So we have a broad range of science that requires very high precision infrared measurements. And if we're to do that, then we need to cool the telescope so that we're actually imaging the sources in the universe that we want to study, and not just looking at a big thermal background caused by the telescope itself. The way you do that is you get your telescope and your science instruments to a very cold temperature so that you're able to essentially image the infrared radiation coming from the universe and not just your own thermal signature. So we're cooling the telescope and the instruments to something like 40 Kelvin, which is 40 degrees above absolute zero. And that's the reason we need this sunshield. Now, all of the infrared telescopes we've flown up to now have relied on essentially a big dustbin of liquid helium to keep them cold, and that's fine, but as you go through the life of the mission, that helium burns off. So you end up with a relatively short lifetime for your mission, a couple of years, and that helium has burnt off, and you no longer have a cold telescope, so you can't do infrared science anymore.
And that sort of happened to Spitzer, right?
That has happened to Spitzer, and Spitzer is now in what's called its warm mission phase. It happened to Herschel, so both of these missions reached the end of their specified lifetime and ran out of helium.
Right.
So what we're doing here is we're using the Sunshield to do what we call passive cooling. That means that we can operate JWST as a facility observatory, hopefully for up to 10-year lifetime, and be able to do infrared science. So that's why we have the Sunshield. We have some real challenges trying to do this science. So, for instance, to image the very first galaxies that formed in the universe, we need a very large mirror, which is what JWST provides. We need to be able to image in the infrared because most of the light from these objects is Doppler shifted into the infrared part of the electromagnetic spectrum. And we also need angular resolution. And so we go to a very large cryogenic telescope, and that allows us to do this kind of science.
Great. All right. Thank you very much. So let's get to the test before too much time goes by. So last summer, you guys, Alberto and Jonathan, you guys pulled this thing out, huh?
Yep.
You guys. So describe the test to us. This is the actual. Now this is the actual Sunshield. This is the one that's going up into space, correct?
No.
This is not it.
This is not it. This is a development article.
Okay.
And so it's typical of how we build these things. We build test articles and engineering models, and as we gradually increase our knowledge and we're sure how the system is going to behave, then we begin to experiment on the flight hardware very gently so that we're sure that it's not been loved to death, if you will, on the ground.
Sorry, your telescope isn't working. It's been loved too much.
And so these membranes served many purposes in the development of the Sunshield. Their first purpose was to essentially pathfind and to prove out the manufacturing processes. I happen to be sitting in Huntsville, Alabama, at the membrane manufacturers today for a meeting on another subject, JWST related, but these membranes were made to start the pathfinding process to prove that we can manufacture them. And then we also learned how to handle, fold, and stow them. And ultimately, when they were secured for launch, release the locks and prove that they would unfold without snagging on anything as a unit. So previously, single layers had been deployed, different pieces, the core, the various folding had been tested, and so this was a little bit like a symphony, where each of the different pieces was a section of the orchestra, and we finally got the band all together to play that one symphony, which was the deployment.
Okay, you guys have sent us some really nice time lapses. Kelly, if you could show us those going on of the actual test itself. Now, you brought up an interesting point with this not being the actual deployment heat shield that'll be deployed.
No, not this video, Kelly. Sorry,
no.
the Sunshield.
Yeah,
no,
sorry.
Here, I've got it. Let me throw it up here.
Oh, there she goes.
That's not it.
That's still the secondary.
That's still secondary. Sorry.
I've got it up on mine.
There you go.
Okay, so these, yes, I see people physically pulling them out. Describe what we're looking at, Jonathan.
So what you're seeing is the deployment of the Sunshield, mainly the mid booms pressing out, and what you're seeing now is the tensioning of the individual membranes, the reeling in of the cables that pull them from their initial position on deployment to their final position. That is pulling them into those V's that I told you about earlier.
Right.
Are an absolutely necessary part of getting the Sunshield to work. So the main objective of this test was to prove to ourselves that we know how to secure the membranes for launch, and that once they're in that position, that they will unfold without snagging and assume the correct final positions.
Okay, I'm seeing a lot of people doing a lot of pulling. Presumably they won't be out there doing the final.
No,
so
but I volunteered. I totally want to be one of those people that go out.
I would do it too, Scott. I'll go out there and do it too.
Here you go. What you see, actually, there were really 13 principal people, 7 engineers, 6 technicians, or vice versa, that were really responsible for that test. And because it was such an interesting and important test, there were a few times more people that wanted to see it real time. So they got to the lucky 13 got to do their very important job in front of maybe 100 onlookers. Yeah. And so there were video crews, myself, Mark, Alberto, any number of people that were interested but not specifically assigned to the test team. That's why it looks like there's an awful lot of people around it, because, quite frankly, there are a lot of people around it.
So this test taught you that you know how to fold them properly for launch, and that they will, in fact, unfold properly once they're ready to be deployed.
Yes.
Anything else? Anything else that you learned that maybe you hadn't expected, or were there any surprises?
Let's see. Actually, it went amazingly smoothly. It's testimony to the many hundreds of man-years that the Team Sunshield has put in to get ready for this point. Some of the things that I know Mark and I are particularly interested in was the behavior of the membranes at the edges. They're actually, very elegant behavior. If you stand at the right point, you can see all the way to the core, indicating that the heat can easily exit the stack on orbit. So I think all the surprises, at least that I got personally, were all quite good out of the test.
How about you, Alberto? Were you happy with the results?
I was very, very surprised. It was the first time, again, we did all 5 layers, as John mentioned, and it was a very complex sort of routine. Falling back to the going back to the orchestra example that John brought up. It was a very, very nicely and well choreographed event that actually took place very well. But the thing I wanted to mention is that we learned that we know how to fold them, we know how to unfold them, and they unfold without breaking, without tearing, without snagging or anything. But at the same time, it's critical that at the end, with their tension properly, they maintain the shape that gives us the properties that we want for the telescope to operate. And I think that was also a key part of the test, and actually that went remarkably well as well.
Mark Clampin, do you have any comments on the test?
Yeah, I was like John, very happy and very pleased that it executed with very few sort of very minor hiccups. Everything went as planned. We were very happy with the way it worked, and as you've already heard, this is just the first step in a sequence of these tests as we add complexity to the deployment test to get to the simulation of what it's actually going to be like when we do the on-orbit deployment. So when you start off this well with the first step going so well, it's always good to know that you're going to be able to move forward through the rest of your test sequences later on in the year without too much problem. So yeah, I was very happy with the way it executed.
So does this mean that we know the answer to the question of how many aerospace engineers does it take to do space origami? Is it 13? And maybe more?
That question's finally been answered.
I've been wondering that for a long time.
Yeah, the 13 folks were the ones that actually were responsible for the execution of the test. Team Sunshield is considerably larger. So I would answer that the number of engineers it takes to do origami is all of them.
All of them, yes.
All of them. So actually, I want to mention something else that perhaps some of the viewers that saw the deployment of the test might wonder. It's like, okay, so you're testing this on the ground. Never mind the hundreds of people that are going around, the 13 engineers that are physically executing for the much larger team. But wait a second, this is in gravity. So how do you compensate for the effect of gravity on planet Earth when you're not going to have any gravity on, in orbit as you deploy? And that's a key question because it takes some, it took some thought.
Yes, it took some thought. The reason that you see those large pieces of plastic underneath the membranes is essentially a first-order simulation of where the membranes will be in flight. If we didn't have those plastic sheets there, it would droop, and perhaps giving us a false problem. What you also don't see is the many hours and hours of analysis. The reason I said all of them is because basically every aspect of the Sunshield, and indeed the observatory, is watched over by teams of engineers that are assigned to each aspect. All of them have to work together for the team to be successful. So my glib comment of all of them, actually, I meant all of them to be successful. But we also have looked at and have run tests in the very same room to convince ourselves that in zero-G, when the membranes will billow up, they also don't run into the telescope or other structure that wasn't included in this test. So we try to think through very, very carefully, what are the differences between our test environment, our deployment environment? Do our test conditions, does our analysis cover it? It can be quite an involved set of questions.
Oh, I'm sure.
Of course, we have some pretty clever and experienced customers that also review our analysis, which makes it challenging.
Good. Well, I'm sure this is the first of many tests, and Alberto brought up a good question that I wanted to ask about this. So you're right. We have gravity on Earth. You're testing on Earth. You will be performing tests in the future that sort of compensate for this, right?
Oh, yes.
And how will you do that?
Let's see. We do it lots of different ways. Maybe now's a good chance to show the secondary mirror deployment video.
Okay, Kelly, can you do
it? The one we were showing before, yeah, because we have the same issues there, and John, I wanted John to talk about that as well.
Yeah, there's a really good example. So what you're looking at here is you're looking down from the top, and as you see the mirror structure, the tripod itself, deploy, it's being deployed by the engineering model of the motor that will do it in flight. And if we can hold it right, let's see, go back to the end of the video. I want to show you one item here.
Go to the end of the video?
Yeah, go to the end of the video and hold it.
Can you do that, Kelly? I know we're asking a lot here.
Yeah, this is pretty hard.
Yeah.
But see, all the people that were in the Sunshield, they're still in there, right? They're going to be all out there helping out.
Yeah, absolutely.
Okay, can you go to the end of the...
I don't know if we can get it or not, but
maybe she can play.
Whether it's resolved.
Yeah,
but
kind of
the secondary mirror mount that you see.
Okay, right there.
Keep going. It's right at the end. Okay. It's actually quite hard to see, but there's actually a cable at the end of the tripod where the secondary mirror will be. And let's see, stop it right there. There you go. So if you look on the top, actually if you look very carefully at the secondary mirror mount, the structure that holds the mirror, you'll see a cable assembly that's pulling up. And that cable is pulling up with the weight of the tripod to essentially make the tripod weightless to prove that the motor can drive it in space.
Okay, so you got cables and pulleys.
This is a very concrete example of offloading, and how we do that and perform the test and not make the test too easy or too hard is one of the engineering challenges that's faced by the deployment team.
Well, Alberto, I have a suggestion for you to put in your innovation group. Instead of using cables and pulleys to simulate anti-gravity, make an anti-gravity machine.
We're working on it.
And so that we could just cancel out all gravity in the surrounding area.
That would be nice. Actually,
it's called
spin-off
right?
technology.
No, we
That's
have
a
those.
spin-off.
Just go on the elevator, just cut the cables. We got those.
Well,
Tony,
I think if you guys figured out anti-gravity, then we've already figured out dark matter at that point. So we can just get it all done in one fell swoop.
I don't know.
That's
So
right.
what
Get
were you
her
saying?
done, Alberto.
Wait, Mark was saying something. Yeah.
Go ahead, Mark.
I was gonna say, you can see as we do these different tests, you can take that video we saw at the beginning, the sort of cartoon schematic of the deployment.
The
And
animation.
we're slowly testing each of those pieces. So by the time we fly, we'll have done all of these tests on the ground multiple times, and that gives us the confidence that this whole process will execute once we're on orbit.
That's a great point, Mark. I'm glad you brought this up because Alberto and I talked to, I believe it was Scott Willoughby back at the AAS last January, and he gave us some really good insight into how hardware becomes space qualified. And can you give us some idea of what that means? I mean, Jonathan's touched on this a little bit. We build this one sort of mock. It's not a mock-up, but it's a version of the deployment heat shield, but it's not the one that's going to fly. Give us some sense of how this stuff is tested on the way to space.
So,
and built.
In order to go to space, every piece of hardware has to be able to survive the environment in which it will be working in once it's in space, and the environment that it will see during launch as it goes into space. So, just to take an example, the whole JWST, once it's been stowed, we'll have to go through environmental testing, which means that we'll put it on a shaker table and simulate launch. All of the materials that go into JWST have had to be tested and verified or validated that they can meet all of the extremes of temperature that our models predict that they will need to see. So we have all the temperatures that they will see during launch, and then the temperatures they will see once they've cooled down to cryogenic temperatures. And some of these pieces of hardware see very large extremes of temperature, and so we have to test for all of those. And then you also have the quality assurance aspect, where people have to keep very solid paperwork on how the piece of hardware was made. It has to be tested, signed off. So there's the whole sort of oversight process of actually putting something together and doing the testing in the lab or at the company that's building that particular piece.
And that's true for every single nut and bolt and anything that goes on this observatory, right? It has to be what's called space qualified, if I'm getting that right.
That is correct, and the reason is that you can't go up and fix it later on, so you have to test and make sure that everything works on the ground the way it's meant to, and not just as a set of individual components, but also as a system.
I actually have a question from Twitter regarding that too. Let me go and show this up here real quick.
Yeah.
This is from, I want to say, Manan Arya. I apologize if I mispronounced that. It says, for the Sunshield deploy test, did you, and how did you, measure the deployed shape? So is there a reason why that shape came into being, and how do you guys measure to make sure that that was the nominal shape when it was fully deployed?
Well, who are you asking it to?
The panel. So I have an innovation scientist on my left, and so innovate, Mr. Conte.
You're at Mantech. Do you want to answer that?
Yeah, I'll go ahead and answer that. The shape is determined by analysis. Which one gives us the cooling that we need and allows the packaging that we have to get it stowed and launched and deployed. We do measure each of the membranes by themselves. The template membranes were measured by a variety of techniques, laser trackers, laser radars called LIDARs, and other instruments of that ilk to show that they had the correct three-dimensional shape. So the shape is determined by analysis. It gives us the thermal and optical performance that we require, and then when the membranes are made, they're measured, and then at that system level, we simply verified that the pull points, the corners of the membranes, were in the proper position.
Okay, so we do have a lot of great comments and questions also on Twitter. Thank you guys for using Twitter. I appreciate it. But before I get to all, and I promise I'll get to as many as I can, I want to ask Mark, how you were talking about the qualifying space hardware, what it takes to make sure that it has to work right the first time. You, as the observatory project scientist at Goddard, how confident are you that all of this is going to work as planned or as designed? Are you pretty confident based on what you're seeing so far?
Absolutely, I'm very confident. As the observatory project scientist, I have to be involved in all of these processes, as John will tell you. So I go out to Northrop on a regular basis and sit in meetings where we discuss how this work is going to get done, then sit in the reviews when we've done the work and we're looking at the results. And basically, I participate in all aspects of this. And I went out to see the Sunshield deploy because that is something that everybody asks about. And of course, as a scientist, I'm very concerned about how it deploys, because it's not just getting it out that's important, but also how it comes out, how each of the layers are aligned with respect to each other has a big impact on the science. So I'm clearly very interested in aspects like this. So yes, I'm very confident because I stay very tuned in to what John and Alberto and the engineers out at Northrop are doing, so that I understand what they're doing and how it's being done, and understand what the challenges are and how we're addressing them.
Well, great. I'm glad to hear that. Now, on a related note, and let's take a little bit step back to the bigger picture for just a moment and look at the mission as a whole and how the observatory is coming together. Can you give us a status, an update on are things going on schedule, or is there any red flags? How are things going with the observatory as a whole?
With the observatory.
Go ahead, Mark.
Okay, let me just speak to a couple of things we're doing here at Goddard, and then John can speak.
Okay, that sounds great.
So one of the big milestones that we're just in the process of reaching at Goddard is something called CV2, and this is a thermal vacuum test at cryogenic temperatures of the 4 instruments. We're doing 3 of these. We are just finishing up the second one now, so for the last couple of months we've been operating the 4 flight instruments, the ones that will fly, mounted in their skeleton, if you like, that we call the ISIM, or the Integrated Science Instrument Module. And they have been operated in a big chamber. We've done instrument-to-instrument alignments, checked the performance of each of the instruments. And we just finished that process recently, and we're now in the process of starting to warm those instruments back up. So that was the second of 3 tests, and that went.
And that's really going on at Goddard right now.
Yeah, it's actually just finishing up right now. Yep. And you can see the challenges I have doing this interview in a green building where the lights keep going out if I don't move. So.
Well, at least we know you're saving energy. That's good.
So the bottom line is that we're doing really well. We're on schedule with our instrument testing. The other big activity we have here is that we have a flight spare backplane, which is what the mirrors mount to, the center section. And we've actually mounted 2 flight spare mirrors on that. And that structure's being ready to be shipped down to Texas towards the end of the year, so that we can put it in the big chamber in Texas at the Johnson Space Center early next year and start doing testing that will allow us to make sure we understand that all our test hardware in that chamber works in preparation for when we send the final telescope down in 2017 for its end-to-end cryo-optical test. So that's awesome. What's going on at Goddard, and I'll hand over to John.
Okay, John, go ahead. Why don't you give us a quick update on how things are going on your end?
In short, we're really quite firing on all cylinders at Northrop. We have accepted the flight structure that's going to hold the mirrors, and are attaching the wings that hold the 3 sets of primary mirror elements that fold back that you saw in the deployment video. We're in the process of building the spacecraft structure, which is moving along apace. Flight boxes on electronics are being received. The main structure of the Sunshield is in build, and we just had the test readiness review to measure the second flight membrane here at Nexolve, and we concluded that yesterday. So basically, all of the hardware for the Northrop side, everything that's not the ISIM, is in some level of manufacture or assembly. And so it's very exciting at this point in the program.
Awesome.
And I want to underscore one thing that I think both Mark and John brought up, which is the fact that at some point, just because you test the Sunshield separately and the mirror separately, it doesn't mean that they're going to work as a system well. And so what Mark was mentioning is that at some point there will be a end-to-end testing of the whole observatory, and so that's extremely important, because just because you test, under these conditions, from launch to deployment to actual commissioning and then through operations, it doesn't, if you test a separate system, it does not really follow through logically that it will work together very well. And so I think all these tests are getting larger and larger in complexity in the sense that you're adding things together. And this is actually the name of the game for this telescope, because it's so complex, but at the same time so beautiful to watch.
I know. This is great. I'm very excited, and I'm glad things are still on track. We have gotten a lot of comments and questions. Let me try to get to some of them now. This is from the Q&A app. Michael Jobin is asking, now when Mike Massimino was removing Kapton on HST, it fell apart when he touched it and made a mess. The sun degraded it. So is that okay?
Let's see. There's a couple of things that are different. The Hubble's in a very low orbit. It's actually still in the sensible atmosphere, if you will. And so the Kapton on the Hubble faces a very different environment. The low Earth environment is much more hostile to us than the L2 environment. That being said, the Kapton and Sunshield material development was one of the 10 early technologies that needed to be developed and demonstrated prior to confirmation of JWST. So the actual design of that flight material saw extensive environmental testing about a decade ago to prove its flight worthiness. So
for its lifetime.
Good question, and again, we answered that question by testing and retiring that risk.
Right.
And so basically, you're saying that it's the amount of atmosphere that Hubble is going through that's slowly degrading it because of friction over that long period of time that James Webb won't be dealing with, since it's going to be out at the L2 point. Is that right?
Correct. We don't have the concern over atomic oxygen, which is extremely corrosive both kinetically and chemically.
Right.
And so it does have the tendency to degrade materials in a different way in low Earth orbit than it does in the essentially interplanetary environment that we're going to live in.
Okay, Judy Schmidt, also on the Q&A app. Hi, Judy. Asked a really good question, and I want to use it also as a segue into the L2 point discussion a little bit. She's asking, is there any place in the solar system where an infrared telescope could be placed and not have to rely on coolant and sun shields to maintain its effectiveness? Is there anywhere we can go where we don't need these things?
Let's see. I'll take a crack at it, and Mark may have a few other ideas. But basically what we need to do is get our telescope into a cold environment. We're bringing that with us. That's the Sunshield. And we want it to be steady, which is one of the positive attributes of the L2 orbit. In principle, we could locate that infrared telescope very far away from the sun and away from its heating, the sun's heat. The problem with that is we then have no power, or very little power, or have to take a very large battery or radioisotope thermal generator or something of the like. And we're now very far away from us, on Earth, and we have to send the data home. So the orbit that we were chosen is a balance between a stable orbit, close to home so we can get the massive amounts of data that we're going to take home in a safe way, and the ability to stay out of the Earth and Moon shadows, giving us a stable environment. So in some respects, it's kind of the Goldilocks place.
Yeah,
that's the best.
Let's talk a little more about the L2 point. Alberto, can you describe what the L2 point is and why we're going there?
So we're going there for all the reasons that John just mentioned. Because We want to face the moon Earth system all the time.
That's what I was trying to get you to say. Okay, good.
And we are going to do that, and that provides us with power because the sun is also in the same direction. That provides us with line of sight, to Earth. That is great if you want to beam down information. And this, as John described, it's basically a sort of a it's not really a point. It's because I think what I would like to notice, if folks take a look at the deployment video at the very end, where after the 29 days, after the month where the deployment takes, there's a very large. You see this orbit, which is a very large orbit at the very end, which is an orbit that is larger than the distance from us to the moon. Really, it's a 800,000 by 500,000 ellipse kilometers, right? Ellipse, and so we are around the point, where we are able to, and there we go, if you show the deployment at the very, very end, you might be able to see those lines represent the size to scale of the orbit around the second Lagrangian point that Webb will take. And so you see that, we see the distance from the Earth to the Moon, and if you keep it running, Kelly, you'll see that at the very end, before it disappears. So you can probably pause it whenever you have those lines showing up in a few seconds. There you go. So those lines represent the size of the orbit of JWST around that point. So it's really not at L2; it's in orbit around L2, and that orbit provides again a very stable point for power, a very stable point for data handling. In terms of beaming down the wonderful data we're going to get in 2019.
Yeah, it's worth stating very quickly that once JWST is launched in the early morning of its launch day, it's never in shadow. We have no eclipses on this orbit. We're never in the Earth or the Moon shadow at any point in our trajectory.
Interesting. So Mark wanted to say something?
Yeah, I was going to say the one other magic thing about L2 is that we get 24/7 science operations.
Exactly.
Yes.
Downtime is slewing from one object to the next, unlike Hubble, of course, which in its low Earth orbit has to go around the Earth, and we go 45 minutes around the bright part of the Earth, and then we get 45 minutes of science around the dark. So at L2, we just get to do science all the time, and it's just going to be very important for doing some of the exoplanet science that people are proposing now, where you may have to spend quite a long time staring at one object.
Glad you brought up exoplanets.
Yeah, exactly. I was going to say the same thing.
James Lindblad is asking on YouTube, and as we've heard, one of the science goals of JWST will be to help us understand exoplanets a lot more in their atmospheres. And he is asking, how small an exoplanet will JWST be able to resolve? Mark, can you answer that one?
Sorry, did you say to resolve?
Yeah, resolve.
That's a key question. That's a key.
Yeah. Maybe we should talk about what resolve means.
So,
that means
JWST will be able to, I guess the word I would use is image exoplanets in the sort of gas giant class, maybe down to some of the larger Neptunes. And this is because we really weren't designed to take direct images of planets. And there are a lot of things that go into the question of how you do that. But the bottom line is that you're trying to look at very faint objects next to very bright objects, so you have to use an instrument called a coronagraph. And on JWST, some of the coronagraphs can do these kind of observations, but you can't see in so close that you could, for instance, see an Earth-sized planet. So you can see all the big Jupiter-sized planets, the gas giants further out.
That's good enough for me. I'll be happy with that. Michael Maxey, also on YouTube, is asking, how durable are the optics? Maybe this one's for you, Jonathan. How durable are the optics to meteor impacts, and how hard, easy is in-flight maintenance? Well, that last part of the question is an easy thing to answer.
Actually, both of those, there's good questions, answers to both of those. I'll start with the second question, because maintenance is not part of our mission. So
that's right.
The telescope does not require servicing to meet its lifetime requirement. And working backwards to earlier in the conversation when I discussed micrometeorite impacts hypervelocity testing that was conducted on the membranes we similarly did those kinds of tests on the beryllium mirrors to understand how those projectiles interact, whether they bounce off, whether they crater, or what they do. And so as a result, again, in the budget that determines the optical figure of the mirror, there is an entry for micrometeoroid degradation, and the budget, which Mark has reviewed with me on many occasions, shows that we meet our wavefront or our optical figure, well past the 5-year lifetime, including the effects of the micrometeoroids.
Okay,
so again,
good. This is. I'm putting up another question that's related. I don't mean to cut you off, but this is actually in line with what you're talking about. Where Jeremy Topolsky is asking about the estimated lifetime of this budget that you're talking about. How long is it supposed to last? You're saying you're designing it for the 5-year mission, but
that's right. We have a requirement to last for at least 5 years. Typically the way you prove that a system will last 5 years is by assuming basically everything that can go wrong and will go wrong, and that you still meet the lifetime requirement. And so in a more nominal case, you get a much longer lifetime. For JWST, the consumable item, the thing that will be life-limiting, is our fuel, not the performance of the optics.
Right.
Yeah.
So, let's talk about the fuel just a little bit. What's it for? How much fuel will it have?
We have a requirement to have 5 years worth of mission fuel. And again, this is sized in an extremely conservative manner. We will be loading, the requirement for 10 years of fuel. There is still room in the tank, so if we have extra mass to spend, we'll fill up the tanks. Again, with a more nominal case, we should far exceed that 5-year lifetime.
Okay, great. I'm sorry I'm rushing, but there's just so many I want to get to. Alberto, this one's for you. Please compare, this is Real Thing 1905 on YouTube. Please compare the James Webb to the Hubble.
Oh, to the Hubble? Okay.
Yeah.
Hubble is as big as a school bus. Webb is as big as a tennis court. Hubble is a visible telescope, which has given us actually 25 years of spectacular images. Next April, of spectacular images that has revolutionized science and rewritten textbooks, I might add. Webb will do that, but we have to wait a little longer. But it's also not a optical telescope. It's not a visible light telescope. It's an infrared telescope.
Okay.
The Webb. Wait, I am not done.
I know. I'm just.
Yeah.
Okay.
Once you get him talking, you better talk.
I know.
The size, as Mark mentioned also, we want to image things that are very, very faint and very far away, or both actually, and so we need a larger aperture. So we are about 21 feet or 6.5 meters versus a 2.4 meter of the Hubble Space Telescope. The orbits are very different, as we talked about. The Hubble is in low Earth orbit. It goes around the Earth about in 90 minutes or so. We are going 1 million miles away, or 1 million kilometers away from Earth at this second Lagrangian point. So it's a very, very different ones. And actually, I would say that Webb really does not even look like your grandfather's telescope, so to speak. As you look at it, we have to expose the optics basically in order to satisfy the requirements for folding and for getting the science done for such a large optical telescope, infrared telescope.
Okay, I'm going to have Scott, if you'd queue up a couple of Twitter ones for me, because I know there's a lot of things happening on Twitter, and you can share the screen on that really good. Let me get Adam Synergy's question out on the Q&A app, which I think is a good one to ask you guys. With such a complex deployment of JWST, is it stressful putting it all together? Anyone had any bad dreams yet about it all going wrong?
Sure,
I was going to say that all I have to say is that John, when the program started, had all these hair.
Yeah.
Really?
I was 6 foot tall when I started this program, and the hair was dark. Yes, absolutely. It's stressful, but it's a good kind of stress. Everybody who's working the team is very dedicated, and the stress is a productive one in that it ensures that everybody checks and double checks. So yes, absolutely, it's stressful. But for those of us on the team, you know, we all have the attitude: give us the ball, we want to make that shot.
Nice.
So
nice.
absolutely, it is. But it's,
according to
you know,
Mark,
a lot of us worked very hard to get in this position.
Yes, and according to Mark, things are going quite well. So great
Yeah,
job, guys. I'm really excited. Go ahead, Alberto. You want to comment?
No, I was going to say that it must be. I was going to ask Mark actually. It must be stressful for him as well as a scientist, and because it is for me, for example, because there's always this tension between engineering requirements and scientific requirements that has to go on and on and on, and so you give up this much and you get back this other much. So the stress for the scientist is a little different than building a telescope, but it's very stressful. I think the stress for the scientist will increase tenfold after the telescope actually becomes operational, to see actually what how it will really operate and what it will deliver.
Great. Okay, so Scott, do you have anything from Twitter? Thank you guys, by the way.
I have a few things from
the
Twitter.
Hubble Hangout hashtag is really doing well. So thank you guys.
Sure. Can you say it 3 times fast?
Shut up.
Tony,
Right. So Summer Ash, who's an astrophysicist from Columbia, was responding to one of the tweets out there that with NASA Webb Telescope, my scope wants to science all the time, science all the time, science all the time.
Oh, anything.
Yeah.
Scott just looks for excuses to sing.
Hey, that's what I do. That's why I drive the internet. I
Is
just
that
need
why
some
you're
cat
here?
gifts. That's why I need
didn't
some
know
cat
that.
gifts to go with it. Alessandro Rosati says, I can't wait to understand exoplanets more with NASA Webb Telescope. Can we break it down into 6 words? So I don't know if you guys are familiar with 6 words. It's trying to break down a concept. My attempt at it was might find other Earths out there. Do you guys want to give a try at exoplanets in 6 words?
Exoplanet in 6 words.
So you didn't know you'd be tested, did you?
Yeah.
I can do it in less. We might understand super Earths.
Now, we might understand.
There you go. You're cheating,
6
Scott.
words. Right there.
Now.
Yep.
We
There we
might
go.
understand super Earth atmospheres.
There we go. Awesome. And there's been a lot of great activity with the Hubble Hangout hashtag from all over the place. Questions and comments. You guys have been awesome.
Yeah, thank you guys for getting on Twitter. We appreciate it. It's usually been the light spot in our conversation with you guys. Also, lots of comments and questions on the various social media channels I was looking at. Unfortunately, we're out of time, and I have to let these guys go. You guys going to come back and give us another update in the future?
Of
Sure,
course.
we'll do.
Yeah, till 2018.
I know. Well, so the next test, right, Jonathan? You're going to be like, I'm ready to do
Absolutely.
another hangout.
We-
All
we
right,
do
and Mark,
lots of tests.
when something happens at Goddard, you're going to let us do a hangout, right?
Absolutely, yes.
Okay,
Anytime.
good. People, I mean, I got to tell you, this is generating a lot of interest. This is one of the most viewed hangouts we've done so far, so I want to thank you all very much. And I guess we'll stop there. That's it for this week's Space. That's
Yeah.
it for this week's Space.
I got
Thanks you all for watching. And keep looking up.
That NASA social and NASA official has been. I'm already seeing some tweets going out, so I want to be seeing you guys tweet, and we'll be trying to gather all those questions and comments up.
So let's go ahead and get started. So the James Webb Space Telescope is being built right now, as we speak, in a lot of different places. It's being assembled at NASA Goddard, but it's being built in many different facilities, one of which is Northrop Grumman, and it is the successor to the Hubble Space Telescope. If you haven't heard about it by now, you will certainly be hearing more about it in the future. It's scheduled for launch when, Alberto?
2018, October 2018.
2018, and we'll talk a little bit more about the details of the schedule and how things are going with it and everything else, but we really want to talk about a really exciting thing that happened last summer where they, for the first time, the folks at Northrop Grumman have tested and fully deployed the heat shield, which will protect the instruments on the spacecraft itself. And I guess in order to give some people an idea of what we're talking about, for those who have never seen it before, we have an animation of what will happen once the observatory is in space, once it's in orbit. And I tell you, it's amazing what's going to happen here. This is when you fully understand all the stuff that's going to happen after the spacecraft. Hello, everybody, and welcome to this week's special James Webb Space Telescope edition of our Hubble Hangout. This week we're going to be talking about a recent milestone that was reached in the building of the James Webb Space Telescope, or JWST for short, as I love to call it. And we have people both from Northrop Grumman and Goddard Space Flight Center to help give us some background and to talk about this latest test milestone. You may recall back in the summer. In their facilities in California, the folks at Northrop Grumman have, for the first time, fully deployed the Sunshield, which will be on the orbiting spacecraft. We're going to talk about that test. We're going to talk about what the Sunshield is, and we'll talk about the overall deployment of the James Webb Space Telescope as well. But before I do that, and before I also get to the introductions of everybody here, let me tell you how you can interact with us. If you have questions about the JWST or the deployment or anything about what it may do, its science, we hope that you will interact with us by either using the easiest way is to use the Q&A app that's either both on YouTube and Google+. Another very easy way to do it is to comment on the event page on Google+ and the YouTube events video page itself, because I'm monitoring all of that. Also, we hope you will tweet at us using the Hubble Hangout hashtag.
Orientation. Once that's done, as you're going to see in just a second, the telescope begins to deploy the secondary mirror mount, the aft radiator to allow the instruments to vent their heat to space, and then finally the wings. And this is completed roughly about 1 million kilometers or 600,000 miles from Earth.
And if you can see on the upper part of the screen, just sort of the elapsed time. We're in day 29 in this animation.
Yes.
So a month after launch, this thing is going to be going through its paces to become fully deployed in its spot at the L2 point, and we'll talk about what that is in just a minute. Yeah. So I don't know if you guys fully got that. I mean, they crammed this whole gigantic observatory into the rocket, and the engineering challenge, one of the biggest ones they've ever had to solve, I think, was how are they going to get something that has the shape of the James Webb Space Telescope into a rocket and out to where it needs to be. And you just saw the plan for it. John, who was responsible for this this design? Was there a group of people, a team of people that came up with all this?
There's a very large team of people that studied it in the early phases and came up with the architecture.
You can also use JWST. We're doing both of those as well. So please tweet, ask your questions, and give us your comments, and we will use them later on. I'm very excited about today because for the first time in a long time, I've got my old friend, Dr. Alberto Conti. Hello, Alberto.
Hey, Tony. It's great to be here again. Long time, indeed.
Used to be an astronomer here at the Institute. Now,
and they stripped him of his rank and sent him out to me.
That's right. And are you still an astronomer? I mean, what are you doing over at Northrop Grumman?
Yeah, I do. My title is a little weird, but I'm still an astrophysicist here at Northrop Grumman, but I'm the innovation manager for business development, so I work on JWST and things that are perhaps in the future after JWST.
Oh, nice. Okay, good. And also with us is the chief engineer from Northrop Grumman, who works on the JWST, Jonathan Ehrenberg. Hi, Jonathan. It's really good to see you for the first time in our hangout.
Hi, nice to be here.
Good. Also, he's back with us, Dr. Mark Clampin. He is the program manager for the James Webb Space Telescope no, I'm sorry, you're not your program manager. You're the observatory project scientist for the James Webb Space Telescope at NASA Goddard. Hi, Mark. Welcome back.
Hi, thanks. It's good to be back.
Okay, and also Scott, driving the internet.
Driving the internet. I will be tweeting all over Hubble Hangout, and I know
it gets into space. It just blows me away every time I see it. So, John, I think what I'd like you to do, if you don't mind, is we have an animation here of the deployment sequence. Can you step us through it just a little bit? What's going to happen to JWST once it launches?
Sure. What you just saw was separation from our launch vehicle and stabilization and unfolding of the solar array. If you watch along the bottom, it shows our position away from Earth, and as you can see, we're passing the moon and still quite stowed. We have a couple of mid-course corrections to add the necessary energy to achieve our orbit, and the blue dot we just left behind is the manned altitude record currently held by Apollo 13. The Sunshield begins to deploy by opening the aft and forward pallets, and the telescope, which was snugged down for launch, moves away about 4 feet from the Sunshield. And what you see is the various covers that protect the membranes unfolding, and the structure, the mid-booms, as we call them, pressing out. They're like a great big old-fashioned car antenna. And then after a suitable waiting period, we reel in the cables and tension the Sunshield, pulling it to its full